Well, my talk, like he said, is the joint range of a pair of inhomogeneous quadratic functions with applications. This is a joint work with Professor FABIÁN FLORES BAZÁN from the University of Concepción. Well, basic definitions about what it's about joint range. We got two functions, quadratic functions, not necessarily quadratic forms because of the linear term and the constant term. These are very general, not necessarily convex. So we got the joint range, denoted by F, capital F. And we got the homogeneous part and the linear part and the constant part. So that we have this equality. The study was born from the fact that there are several Farkas-type lemmas on the literature about quadratic forms. You know the classical Farkas lemma about systems of linear equations, but on this context of quadratic forms or quadratic functions, it was very hard to get such results. So these Farkas-type lemmas, known as S-lemmas on this literature, show that we have a hidden convexity property, which we have to look for. And that is where this work was born. A few properties, which are central fundamental properties on this work. Non-degeneration property, a very strong one, means that these functions, the quadratic part of the two functions, has no common zero except by zero, by the zero of on the Euclidean space. And the simultaneous diagonalization property, which is very used in the literature because it offers a nice way to get through linearize, in some sense, this problem. Namely that the two matrices can be diagonalized at the same time. Well, the key theorems is the classical result of Dines, which is a very nice one. It stated that two quadratic pure functions, the image set is a convex cone. And when the dimensions are so big, and we get the non-degeneration property, which is a very strong one, we got the pointedness of this cone. And then we get this result from Ramana and Goldman, which stated a characterization of the convexity of this set, which is again a very strong one because this set, remember with the linear terms, has no necessity of being convex. So this is a characterization which is a very strong one. So like this set is not necessarily convex for all cases, we try to add something. Something is that is array, a single array, which is the less set, which is the least set in some sense. We can add to the set, original set, in order to get convexity. What? Do you miss that part? Are defined, maybe you can, yeah, maybe you can get this earlier. So we're going to study this convexity, the convexity of this set, which is a weak property that the original one means the convexity of the whole set. Well, we go stage by stage, studying first the image of just n when n is equal to 1, the one-dimensional case, in which case we have only four possible forms of the set, namely just a point, just a ray, a half line, or maybe the famous parabola, or oriented in any way. Okay? So this set is quite elementary, and we get the following characterization of convexity and convexity of the set that interests us. Namely, it's convex when only when and only when the homogeneous part, which is the one that dominates the set, is different from minus the direction we got to add. So when the direction and this are linear independence, have linear independence, we got something like this. Okay, this set is just a line, but when we add the ray, we get all this new set, whole new set. So we get convexity. Okay, which is not true when the homogeneous part is the contrary of is in the opposite direction of the direction we must add. In that case, it happens something like this. It's like the complement of the convex whole of the original set, okay, which is non-convex. So studying the one-dimensional case was a very fruitful one because allows us to study the most difficult case of n equal to 2, bidimensional case. We get some characterizations of the main properties. This is a very strong one. Look, a closed set different from a line. And as the property which this equivalent condition is a very natural one, and this not. Well, how do we get these characterizations? By studying carefully all the possible forms that this set can have. Because we know by Dinner's result that this set is a convex cone. So on the plane, we don't have much choices of a convex cone. So we study all the possible ways that this set can have and discarded all the ones that couldn't, and we have the ones that the set can attain. This draw will look like draw by a 5-year-old kid. We look all the possible images. Okay, a point, array, a pointed closed set cone, which is not array because that was analyzed. A straight line, an open half plane, which means an open half plane with this because we need to add the origin of the plane, okay? And the whole Rn, the whole plane. We discarded some cases that can happen that a convex cone can have on this, that a convex, by example, this set is the open half plane plus this line, which is not analyzed there, because the set that we are studying cannot have this way, this form, because this ray allows us to conclude that we need more dimensions to do this. Okay, so it is discarded. We get a few more, but we don't stop there. And after we get all the possible forms that this ket can have, we study the SD property, the ND property, which these two are related, this with this and this with this. And this interesting property, the intersection of the kernels of the matrices, original matrices, and if the set has a topological interior. Okay? why we are doing this? Because the principal aim is to do this. Given 2 points of the image, we need to insert this expression onto the joint range. Okay? This point on the joint range. But we can do this in all the cases. But when we can do, we just need to include them onto this, onto the bidimensional projection of these 2 points. Okay? So that's why we're studying carefully the case when n is equal to 2. So we get the main results when n it's like anything. This set. Using this, using the previous case, we get this convexity hypothesis, namely conditions that imply the convexity of this set alone. Okay, this is quadratic plus linear plus constant term. Not studying yet when adding the array. Okay. These are very strong hypotheses, and in order to study when this set is not convex, we need to deny them, naturally. So this one, by example, gives us that the set can only have 3 ways. A trivial one, which is a point, an array, or a half plane, or a half line. Okay? These are the only sets that has empty interior on this context. So this allows us to conclude that when the set is not convex, non-convex, we need to have some linear dependence between the matrices. Okay? Well, B, which is a very strong property that can be expected because all the examples when the set is not convex, I noticed that the 2 matrices are linearly dependent. So I start to guess that have to happen always. Okay, which is true. The proof of all these 3 properties, in some point, happens to sum, the usual Minkowski way, these 2 sets. This for the first property, this for the second property, this for the third property. A parabola, any way that this can have, plus a line or another parabola, or a half plane. Okay. That was the idea of the roof. And that allows us to get to the main theorem, a characterization of the convexity of this set. Okay? Here appears the property that I mentioned before. This one, a very strong one. So, with the main theorem, we get some immediate corollaries. This is the simply connectedness of the set. A property that we can expect because the elementary nature of the set, namely just quadratic functions. But we are only able to prove that after the main theorem. And this one, in particular, this is always convex for any data. And I mention it because this was the starting point from the work, the conjecture that this set is always convex. Okay? It turns out to be true, and then we get weakness of the assumptions in order to get here, okay? So, having this main theorem, we can give a geometric characterization of the non-convexity of this set alone because of this, because the first property. So this set can have only 4 possible forms, namely a parabola oriented on the opposite direction to the direction we add, a parabola with all this full field, the whole plane, less this half line, plus the origin, and the same that before, plus this direction, okay? So when the set is, this set alone is not convex, only one of these 4 ways is present, okay? Except by rotations, because given the direction, or scalarizations, or any other things. Using the, we can, so applications of the main theorem, we get the expected Farkas type theorem, namely a S lemma, assuming a Slater condition, and the denial of the 4 conditions for this set is convex. Then we get the alternative theorem and S lemma. We can mention that a condition like this appeared earlier on the literature due to Moret, a classical work of Moret. So this setting contains the Moret one, okay? And naturally, after the S lemma, we get the strong duality, the same hypothesis, namely the set, namely this set is convex, and a Slater condition, we get the strong duality property, and most important, the characterization of the convexity via strong duality, okay, which is a thing that can be expected because the previous result have this same way, except for the convex cone present here, convex cone of all this, okay? So we have weakness of the assumptions. And an alternative existence result with known, which is proof, is not depend on all the previous setting that shows in a better way the strongness of the non-degeneracy property, okay? Non-empty and compact. So future work, the infinite dimensional case, not just the Euclidean space. We can mention that this property clearly need to be held in the infinite dimensional setting. More than 2 functions. The case where we have 3 functions, the joint range of 3 quadratic functions, it's a very tough one because there are so many geometric ways that the forms that the set can have, okay? More general functions, namely polynomials or continuous functions, getting from the Euclidean space to a lesser set, and some sensitivity analysis based on using this fact, okay? Variation of the perturbation of D can have, we can study sensitivity analysis. And finally, I would like to thank this beautiful institute, the Congress, the University of Concepción, and my professor, who's the main author of the paper associated with this work. The IMPA, I would like to thank personally to Professor Yusem because he shows so many concern about me. And he's always, that's a thing that we can thank always, the Congress we can show some bibliography. The main result for Dines, which he sent to the magazine the December 31 of the December 31 of 1940. So that was his way to celebrate the New Year. S-lemma, Moret, Romana, Goldman. This is a careful study of the S-lemma, which is in some sense contained in our work because of the convexity implied the S-lemma. And the manuscript appearing soon. Well, I would like to finally salute my friends who's watching me via streaming. Thank you.
Remarks or questions?